Hi, and welcome to October 1st, 2018, according to Pete. Yeah, there's that. Okay, you're gonna see me like this for probably a couple of episodes. I had a little oopsie on a skateboard. Broke my arm, hurt my wrist, a whole bunch of stuff, but the show must go on. I did this injury 2 days ago, but I'm here because you're the most important thing, yada, yada, yada. So we're gonna do an episode of According to Pete. Before we totally get going today, watch to the end of the episode and I'm going to give you a chance to win a Digilent Analog Discovery 2 USB oscilloscope. All right, it's sweet. It is my tool of choice when I have to do on-the-move logic analyzing or signal analyzing or such. So this is a really cool thing. You should watch it. Watch to the end or just skip to the end, whatever. I tend to blather. Today, I want to talk about digital circuits. And if you're a Venture Brothers fan, you know what I'm talking about. Now, I tend to be an analog guy, so I tend to steer away from digital stuff. Why? Not because it's not useful, but because it's kind of boring. Okay, let me qualify that. It's not unuseful. Digital circuits are incredibly useful. They're great for determining conditionals, and when you scale them up, you can do all kinds of crazy stuff. And we'll talk about that as we go. But as an analog guy, you look at a singular digital circuit, you're like, I can't use that. It's only got 2 states. It's either on or it's off. Well, that's the magic of a digital circuit. It's only got 2 states. So what I want to cover today is some of the rudiments that are behind that. We're going to talk about some logic functions. We're going to talk about the circuits that make them happen. We're going to talk about TTL. We're going to talk about CMOS. We're going to ultimately look at the functions of those circuits electrically, and we're going to break down a set-reset flip-flop, a clocked one, and it'll be cool. And at the very end, we're going to talk about 7400 series logic parts, etc., etc. And that's a little bit of foreshadow that's going to take us into the giveaway for the Analog Discovery 2. So let's look at some rudiments. So before we get too very far into this, I am going to assume that you know some things. So for example, if you don't know anything about bipolar junction transistors, BJTs, or MOSFETs, it would be helpful if you had that background. I'm assuming you do. If you don't, there's a couple of links in the blog post that will take you to the videos that I've done about those. Some biasing configurations and makeup, yada, yada, yada. Okay. So to set our baseline here, again, digital circuits, there's only 2 states, right? Now you look at circuitry through an analog eye, and you know, with an analog concern, you have a lot of things. Analog happens in real time, right? And it's a fire hose of information because you need to know what's happening at all times, what's happened in the past, and then predict what happens in the future a lot of times, right? Well, with a digital circuit, you only have 2 options. Now that's not to say that you can't deal with this stuff. It turns out that when you get a whole bunch of digital things together and you split time into really tiny parts, you can do amazing things with it. And we'll talk about some of that as we go. But for the basic levels, if you're only trying to do something like with 1 or 2 conditionals, digital circuits are awesome at conditionals because you've only got 2 states. You got low and you got high. If something happens, you indicate this. If it didn't happen, you indicate it's a low, right? Very simple stuff. Because it's so simple, biasing and impedance concerns aren't really a thing. It's easier to make a digital circuit function, at least a small one. It gets very complicated as you scale up, but for small purposes, it's not that bad. And in fact, you can make digital circuits that will address simple conditional issues out of discrete components very easily. Now, will you do that? Probably not. There are monolithic parts that will do this for you. Nonetheless, we're going to go through it and check it out, all right? How do you achieve this electrically? Well, with discrete components, there are a variety of ways you could do it. You could do it with BJTs, you could do it with MOSFETs, you could do it with just passive components. I've seen it done. If you go looking on the internet for these things, you will see a whole bunch of circuits for how to achieve a logical function with just passive components. Now, as I go into this, I want to say, I am assuming that you have some background or know how logical functions work. Not electrically speaking necessarily, but you know what a NOT gate is. You know what an AND gate is. You know what the logical function is, right? So if I draw that, you know that's an AND gate and you know the truth table. If you don't, post a comment and we'll get you some references. That's not a problem. Or you can Google it. But for how you achieve this electrically, now, background inverter. Okay, this is an example of an inverter made from discrete components. Just for your information, NOT gate, it's the opposite of the input. If I put a 1 here, I get a 0 out here. If I put a 0 here, I get a 1 out here, okay? The output is not the input. That's how that works. All right. Now, the way this works electrically is like this. When you pull this guy low, what you have, kind of turn this thing 90 degrees in your mind, but you've got a circuit that is base current up to your positive voltage, okay? And when that happens, this turns on and it pulls this guy's input down, all right? Turning this off, so this becomes a high resistance, which makes that a high. Low equals high, okay? In the opposite direction, it does something kind of cute. Describe. Okay, so that was low. Now, if we pull this input high, check this out. This junction turns off, right? So this is a plus V. Now, remember, this is a BJT, which is effectively another diode, all right? So what happens is you end up with positive voltage, resistor, diode, ground. So this guy turns on, all right? And when this guy turns on, this becomes a low resistance and your output goes low. Pretty cool, huh? That's an inverter. Now, this circuit will work in a pinch, for a really simple, I need to know the opposite of something that happens, right? But it's not ideal. In fact, being that this is the case, it'll sink current real nice. That's not a problem. But sourcing current, it's going to source it through that 1K. So if your input impedance to the next stage is like 2K, which is not unheard of, you're probably going to have some threshold issues. So if the last circuit wouldn't work for you, you can do this optionally. This is a little bit different take on that inverter circuit to make it a little bit more palatable. Now what we've added here is actually called a totem pole output, and it is this guy here. What we've also got here is a little concertina action. Let me describe how this one works. Basically, same way the first one works. Oh, incidentally, when you pull this high or low, it's called a steering current. I kind of picture it like you're pushing a wagon backwards. I don't know, maybe you guys don't get that. But basically, again, when you pull this guy high, this turns off and you're running through this junction, so this guy is still on. When this guy is on, this resistance becomes low, and so the current increases through the concertina section. That has the effect of raising this voltage with respect to ground and lowering this voltage with respect to ground. Now, remember, as I'm saying that, the voltage across the component itself is increasing, but with respect to ground, that point in the circuit is going down, okay? Now what happens is, when you bring these 2 points close together, this guy will turn on and this guy will turn off. When this guy turns on, small resistance here, that value goes low, right? Did that work? I'm gonna look back and see. Yes, I said high the first time, low out. Hooray, I did it right this time. Now when you do it the other way, it goes the other way, right? So when you pull that low, you basically pull this guy low, this guy turns off, making that a big resistance. When that transistor becomes a big resistance, current goes down. So voltage at that point in the circuit is going to go down, and voltage at that point in the circuit is going to go up. When that happens, this guy will turn on, this guy will turn off. So you got a high resistance here, right? Big resistance. It's going to make the output go high. Low resistance there. Now, this resistor is only here to limit the current out that it can source. That's the idea anyway. So this is an improvement with regard to your output impedance. But there are other issues with this circuit. For example, switching time. This is not a particularly fast circuit, okay? Bipolar junction transistors take a lot of time, oh, 4 of them, take a lot of time to turn on and off, right? There's a lot of charge in the junction that you have to get in and out of there in order to turn it on and off. Now, for us analog people, we live life in the second realm, which is really easy to accommodate. But when you're doing like high-speed digital stuff, this ain't gonna fly. Now, another thing that is wrong with this, as you can see, we've got this action. Well, when this switches, there's a very small piece of time where this is on a little bit and this is on a little bit. And when that happens, you're dumping current from top to bottom with very little restraint. Now, of course, there is this resistor here that's for current limiting. Okay, fine. But it's an issue, right? When you try to scale something like this up, this kind of thing becomes extremely problematic and it will suck your power and suck everything. It just sucks. Now, in order to alleviate some of that, what they have done, or what is typically done, is a diode goes between these. And what happens there is that it raises the turn-on voltage of this component. So there's less time that it's actually turned on, okay? Now, this is an example of TTL logic. What's TTL? Most of you are not asking this question. TTL, very poorly written. TTL stands for transistor-transistor logic, and it is characterized by the use of bipolar junction transistors, and generally with a power supply of around 5 volts with associated thresholds that we're not really discussing right now. TTL was really popular back in the day. You know, before I got a 4-year degree in engineering, I went to technical school, and we learned digital logic using TTL parts, discrete or monolithic parts that have this function. You're almost certainly not going to build this out of discrete components. You're not going to take resistors and transistors. You could, but you probably won't, because you can buy something like a 7400 part, right? And we'll talk about that as we go. That will do this function for you. But TTL is slow, it's power hungry, it is a little bit noise sensitive, and we'll talk about that as we go, but it is not the optimum solution to do this with. It doesn't scale well, it sucks a lot of power, yada, yada, yada. Now, if you switch these to CMOS parts, a whole bunch of magic stuff happens, and that's what we're gonna look at next. Okay. One more thing, I don't wanna forget this. It may not be relevant, but it's really cool. This is an inverter, right? Well, now it's a NAND gate. Okay, I don't know about you guys. I can't think of a use for a dual emitter bipolar junction transistor, but man, I want one just to play with. In fact, if I can get it with a dual base or maybe 3 collectors or 4 collectors, I would love to play with such a thing. I don't think it's available. I did go looking. If you guys know where this is at, you let me know, because I want to play with one. All right, now we're going to look at the other circuit. Okay, MOSFETs. When you go to MOSFETs, some really interesting things happen. Now, we've got 2 circuits drawn here. One is a NAND gate, one is a NOR gate. And for reference, I have put the truth tables down. Now, a NAND gate, basically, nothing goes, the output doesn't go low until you've got both inputs high, and that'll bear out in the analysis here. For a NOR gate, the output is high only when both inputs are low, okay? Again, this will bear out in the analysis. So what we're looking at, if you remember the last topology, this kind of looks like the totem pole output. It's just directly driven, okay? Now, as far as function goes, what we're looking at here in the circuit, these are N-channel MOSFETs. These guys are P-channel MOSFETs, as indicated with the little bubble, meaning inverted, okay? And you can see that between the NAND gate and the NOR gate, all that's really happened is it's been flipped upside down. Okay, we'll take that as it is. Now, if you look at the way this circuit is structured, it'll become clear how it works pretty quick. right? A and B are only allowed to go high and low, not any voltage in between, right? So these parts are either on or they're off. And because they're MOSFETs, they switch really quickly. We'll talk about that in a sec. But, let's see, you look at this guy, and you've got, okay, so I've got a resistance in this section, and then I've got a resistance in this section. In order for this to be conducting, and therefore a low output, both of these inputs have to be high. And with both of those inputs high, that plays out, your output is 0, right? Truth table, it works. Now, conversely, this section up here, which represents our other resistance, these are PMOS, right? So these start conducting when you pull that low. And in fact, being that it's a parallel circuit, this whole thing is going to be conducting when either of those are low. And if you look at the truth table, yep. So this is pulled high anytime any of those is low. And that's a NAND gate. Now, on the other hand, it just flips upside down. The bottom section is, again, NMOS parts. So this is going to be conducting anytime either A or B is high. So anytime A or B is high, this output is low. It's conducting. It's pulled to ground. And on the upside, the output is pulled high. Remember, these are PMOS parts. Anytime both of these are pulled low. So when both of these are pulled low, this turns on and that output should be high. When both of them are pulled low, output is high. And that's how that works. Now the improvements from the previous circuit are, I mean, number one, we're using MOSFETs. So like I said, the switching time is much better. Your input impedance is also much better because there's no steering current, right? These are just voltages. And so, you know, very little charge in the junctions. They switch on and off really fast. And consequently, I mean, you know, not only is your input improved, your output impedance is reduced, so it can drive better current. Right, because the switching time is so short, it's dramatically shorter in fact, the time where this section and this section, or this section and this section, the time where that is on and dumping current from your power supply to ground is much reduced, right? And in fact, if you think about it, that little switching time, right? And I draw it this way because, look, all parts live in the real world. Ultimately, every single part, every active part, everything you've ever seen that's electronic is an analog part. But it's only analog from about there to there. And that's where all the trouble happens for digital circuits. So when you shorten that time, which this effectively does, it's less susceptible to noise, it doesn't suck nearly as much power, and because of this improved circuit, you don't have the passives, right? You don't have to worry about resistors or capacitor. Well, that's another story. We'll leave that for another day. But switching these to MOSFETs makes this time really short. And because the circuits are so much smaller and more compact, they scale really well. Now, again, you're probably not going to try to build this discretely because you don't have to, right? These circuits are an example of CMOS technology, which stands for complementary metal oxide semiconductor. And CMOS technology, I really should just do an episode on CMOS probably. But it is a method of fabrication that allows you to place P-channel MOSFETs and N-channel MOSFETs on the same die, okay? And so all of this stuff gets put on the same part, and it scales really well because they're only putting these parts down. So it has enabled us to do things like, you know, make all of our logic gates into a monolithic part like that, or build an FPGA or a microcontroller or a microprocessor, or all kinds of really crazy things that incorporate all of this stuff. Because ultimately, and this is one of the points I wanted to make, it's probably obvious to a lot of people, but let's state it. When you break down reality, right, you've got, right, analog is a fire hose. You've got a signal that's indicating everything that could be happening in the world. But when you break it down, when you take reality and you split it up into tinier and tinier pieces of time, with greater and greater measurements, and then ramp up your clock speed to the point where you're looking at every individual frame really closely, really quickly, you can build entire representations of reality that are far beyond what anything analog could do. And it allows you to do all kinds of wacky analysis, and this is where a lot of people live these days. And it all comes down to CMOS. So there's one more piece I want to touch on before we move on, and that is to talk about this guy, the humble flip-flop. Now, what I've got drawn here is a SR flip-flop, also goes by the name of latch. It could be called a latch, it could be called a bistable multi-vibrator, right? Back from your 555 days, you might remember that term. This is a bistable multi-vibrator. Now, the reason this is so cool is because it has memory, which is not... This concept has been around for like 100 years, okay? But what makes it special is, yeah, memory, but also in electronic form, we can make it really, really tiny. Now we can have lots of memory, and that enables us to do a lot of things. Okay, so let's analyze this as best we can. Now, for my own sake, as well as yours, I've got a NOR gate truth table up here. And a flip-flop is made up of a pair of cross-connected NOR gates, okay? Which is why we have this. Now, in order to analyze it, let's first make a couple of assumptions. Number one, we'll say that both set and reset are in the low state, all right? And if they're both in the low state, either one is in the low state, we'll talk about that. Now, also assume that Q naught is in a low state. Now, if Q naught is low and reset is low, you've got two low inputs. Well, when a NOR gate has two low inputs, you've got a high out there, okay? So Q is high based on this. Now, this is a static position. It'll maintain this as long as I don't do any shenanigans out here. Q's gonna stay high, Q naught's gonna stay low. That's memory. All right. It also happens to be the set condition. Let's say, for example, now, and this is an unclocked circuit, so it's just going to follow the inputs in real time. Now let's say I take reset high, right? So now this is a 1. Well, if I've got a 1 and I've got a 0 input to this thing, so I've got a 1 and a 0, so I'm going to have a 0 on the output of here. Now if I've got a 0 here and a 0 on set, my output is going to be 1. Oh my gosh. So suddenly, I've got Q being 0 and I've got Q naught being 1. That's the reset condition. And now you can take reset low and nothing will happen, right? And so to get it the other way, you just set high and it toggles the whole thing the other way. Then Q will go high and Q naught will go low. And nothing will happen as long as you don't do any other shenanigans out here. It'll just hold its state. Now, one thing about a set-reset latch, you can't have both of these inputs high. Not allowed. Why? Because the output becomes unpredictable. So you will always see this, not allowed. So that's a set-reset latch. Now there are also, you'll also run into JK flip-flops or a D latch. Now a D latch is just like, because this no dual 1 situation is kind of nonsense and you're not gonna, it's a pain in the butt to send 2 signals to make a thing happen. So what'll happen is you'll get like a single signal that we'll call D and it will split, right? So you'll get one that's high and one that's low and it becomes a D latch and clocked. Now let's look at this thing as a CMOS circuit and clocked. Check this out. Now this is a clocked set-reset latch or flip-flop or bistable multi-vibrator. Now before you freak out on this thing, which you might be prompted to do, look for the patterns that we're already expecting, okay? You already know that this is made up of a pair of NOR gates. Now, you'll notice clock. Clock is here, clock input is here, clock input is here. If you take out the components that are attached to the clock, this literally looks like the cross-connected two NOR gates, right? You can see, if you take that guy out, you've got like these guys at the top, and you take this guy out, you've got these two parallel to each other. Now, to describe its functionality, like first, I promise you it's going to work just like the regular flip-flop does, only clocked. What the clock does, basically, is disable the thing until the clock is high. And so things can only happen when the clock is high. When the clock is low, it holds its state steady so that whatever's going on the set and reset lines doesn't have any impact. That's the whole point. All right, to look at this a little closer, let's assume that the clock is in its low state, all right? When the clock is low, and we'll start on this side, when the clock is low, this guy is not conducting. When this is not conducting, it basically disables the function of the reset line, okay? Now, again, clock is low, so this guy is turned on, which disables that input again. Now, if you look at the other side, same sort of thing happens. When the clock is low, this is not conducting, this part is not conducting, so it's disabling the set line. Same thing as this one. When clock is low, this guy is conducting because it's a P channel, and it disables anything that the set line can do. So when the clock is low, it's just maintaining the Q state, right? These are conducting, which keeps the circuit energized, so your Q is going to stay solid. Now, when the clock goes high, just the opposite. This turns off, this turns on, and same on the other side. Now your inputs are active for the time that the clock is high. High, yeah, high, low, I keep doing this. And that's basically how a clocked set reset latch works. Now it gets more complicated as the circuits scale up, but this basic circuit represents so much in what we can do digitally. This has memory, this scales, it goes really fast. Suddenly we've got human evolution. It's crazy. Okay, so that's basically what I wanted to cover today. Now, I realize that there are a whole lot of digital concepts that did not get covered, but I wanted to look at the circuits that do this electrically, right? That's kind of where I like to focus. And I want to give some rudimentary material before I progress down this path. So honestly, I'd like to do a video on CMOS. Maybe adders or counters or something like that. In fact, I would ask you, Internet, if you've got some ideas of what would be good to cover here. You know, would it be an adder? Would it be a counter? Digital circuits that we could do some analysis of that could be fun, right? So if you got some suggestions, put it in the comment section. Now that is not what I want to get the analog discovery to. We're going to get to that in a second. But first, I want to talk to you about parts availability. Now, as I'm doing this, and I'm describing discrete monolithic components that do this sort of thing, there might not be a lot of cause for those sorts of things anymore. Now, 20, 30 years ago, when I went to school to be a technician, and I got a 4-year degree long after that, but we learned digital logic with, you know, the old friendly 7400 parts, right? The 7404 inverter package, I think 7408 was an AND gate. Package, you know, all the old favorites that probably a lot of you remember. But times have changed, right? And so I'm looking at this going like, well, I wouldn't use discrete monolithic logic parts. Why would I ever do that? I mean, these days you get a microcontroller or, you know, maybe an FPGA or something else, something that packs a lot of logic ability into a small package and allows you to change it on the fly without having to resolder something, right? If you're building circuits out of discrete monolithic parts, you are wiring things, hardwiring things. If you jack that up, you get to do that circuit all over again. But if you do it on a microcontroller or something else that incorporates all of this logic compacted into a very small place, you just write new code. It's so much easier. And so I'm kind of at the point where like, I wouldn't mess with these things. They're quaint, yeah. And so I went looking, right, how many of these sorts of parts are still available. And you'd be amazed. Well, if you're not working in that field, you'd be amazed. In fact, you go to DigiKey. Check this out, right? Cassie's going to let me hold my notes because I can't remember anything. If you look at the discrete monolithic parts on DigiKey and gates, right? There's 1,425 singles and quads, like single package AND gates combined with quad package AND gates that you can still buy. This is nuts. NAND gates, 1,667 singles and quads. And these are all stocked parts. These aren't out of stock parts. They're in stock parts. You can buy them today. Nuts, right? Your inverters, almost 3,000 choices. What? Where are these going? Now we're getting to the analog discovery part. So I went asking my cohorts here, what do you think these are used for, right? We were sitting around having a barbecue, like, what do you guys use these for? And this is what we came up with. Legacy designs that aren't cost effective to redesign with a microcontroller or other part. Low power applications. I don't know how much I buy that, but okay, we'll throw that in the list. Education, all right, undeniable. You would use these to describe elementary logic, and it would work really well. And various odd examples where you need to invert a signal or gate, right? Like small type stuff, right? That's what we're talking about. This is where you come in, Internet. I want two things from you, all right? First of all, I want to know for real, where are these things going? If you are working with discrete monolithic parts and you know where they're going, I want to know where they're going. I want you to educate us. Tell us where they're at. But that's not for the analog discovery 2. The second thing I want from you, I want unusual things. I want creative uses for these parts, right? If you weren't working in that field, what would you use these things for? Now, what we're gonna do, what I want you to do, I want you to come up with something. It's gotta be unusual, wacky, weird, crazy, but it must be functional. If it's not functional, yeah, I wanna line my car tires with 7404s and drive around town for greater traction. No, that doesn't work. You'd have to wire them up with LEDs. I did not just give you that one. Forget that. Boy, that's a really good idea. So what I want from you is creative ideas for use of monolithic discrete logic parts, okay? Now we're gonna let this thing soak for 2 weeks, right? So video posts on October 1st. On October 15th, 2 weeks from the date that this video posts, I'm going to look at comments in the YouTube comment section, okay? Not the SparkFun blog comment section. For the Analog Discovery 2, I want you to post your answers in the YouTube comment section. And I'm gonna look at upvotes, but ultimately, I'm gonna be the judge. I'm gonna say which is the coolest answer, and I'm going to give the Analog Discovery to the person with the coolest answer by my rights. Now, I may feel very guilty that day and go, oh, they got a lot of upvotes, I'll give it to them, that's fine. Or I'm gonna be like, no, that sucks, that needs to be more creative. I don't know, it depends how I feel, but you'll get a free part anyway. Okay, what am I forgetting? 2 weeks, YouTube, vote for your faves, and I think that's it. I cannot wait to hear your answers. So, thank you for tuning in. If you've got any questions or any suggestions, again, more suggestions about videos that we could do about circuit topology and analysis. I love doing that stuff. So if you got some requests, I would love to hear them. And yeah, in 2 weeks' time, we will announce on our social media channels and probably on the blog post, because I think I have the blog post for that day, we will announce who wins. And then we will contact you and we will send you this Analog Discovery 2 and you are gonna dig it. And that's all for today. Thank you so much for coming, and I will see you next time. Goodbye. Hello? Hello? No. Hi. Damn it, I have to do this again. I need to look at my notes again. Oh, you might have to cut this. We'll analyze it. In fact, I've already jacked it up. This is actually my 3rd time running through this circuit. I didn't hit my head, but I feel like I hit my head. Stop on. Oh boy, I need to back up. We can cut this. Oh, stop.